Hello, everybody. Good morning. So, before I get started on today's virtual lecture, I just want to make two different announcements here. The first one is that I am still in San Diego, of course, and I won't be back until Wednesday night, which means that today's lecture and Wednesday's lecture will be a virtual lecture. So, be prepared for that, just like this one on video, where you can copy notes down as I'm talking and lecturing on the video. And then the second announcement is that today's lab will be, as it's scheduled in the calendar, is a project day. And so you should have already completed your HPLC experiments, and so I highly recommend that since today is scheduled to be a project day for your lab, you should get as much of your semester long research project done as possible. Okay? All right. So I'm going to go ahead and get started, and we're going to start talking about NMR spectroscopy now, which is the final, like what I like to call a light method or a electromagnetic radiation based method, right? And we didn't get to talk about that on the last exam, but we'll start it now. And so both today's lecture, part one, will be today of NMR spectroscopy, and then part two will be on Wednesday, also on video. Okay, so NMR spectroscopy. Okay, NMR spectroscopy, right? So how do we start this, right? Well, the first thing is what exactly is NMR, like nuclear magnetic resonance? Okay, so let's talk about what that is. We'll talk about very basically what it is, right? Many or certain nuclei possess an effective nuclear spin, resulting in a magnetic dipole. So what does this look like? Well, if we draw a nuclei that has a positive charge, right? Because it's a nuclei or nucleus, and it has a spin, we'll call this a spinning nucleus. Right, we'll call this a spinning nucleus. It has a dipole. Magnetic dipole. So if we apply an external magnetic field to this spinning nucleus, right, what will happen is that the nuclear spin, what will happen, right, is that the nuclear spin will either align with or against the external magnetic field. So what does that look like? Well, if it's aligning with the magnetic field, this is called the alpha state. And this is the lower energy state. And if you're aligning against the magnetic field, this is the beta state, and this is the higher energy. This is the higher energy state, right? So now that you kind of have a basic knowledge of what's happening in nuclear magnetic resonance, right? Let's talk about. I think it's important to talk about the nuclei that we study in nuclear magnetic resonance, right? So commonly studied nuclei include things like proton, NMR, or carbon-13, NMR, or fluorine-19, NMR, and phosphorus-31, NMR, right? So the thing I want you to notice about this is that all these commonly studied nuclei have odd mass numbers. And that becomes important in a minute. Okay? So let's take down some notes here. Let's take down some facts to know here, right? Nuclei with odd mass numbers have a spin number or I. Okay. And so I can equal things like 1/2, which is the easiest and probably most common, because would be our nuclear dipole. But we also have things like 3/2, 5/2, and 7/2, and so on, right? Which are all greater than or equal to 1. And so these would actually be considered, right? These would actually be considered nuclear quadruples. Nuclear quadruples. And so we'll talk more about the nuclear quadruples later, right? But let's just, ask ourselves then, what does it mean then to have it be a nuclear dipole, right, as far as spin states goes? So for I equals 1/2, you have the spin states of plus or minus 1/2, right? Or up or down for the spin state, right? Arrow pointing up or arrow pointing down. Or if you have an I that's equal to 3/2, this gets a little more complicated because our spin states are 3/2 and 1/2, plus or minus on both, right? So what are some other nuclei with odd? What about other odd nuclei with odd mass numbers? Other nuclei with odd mass numbers, right? Namely, the one here would be nitrogen 15. Right, nitrogen 15. And it has a I that equals, I'm just going to write that again, nitrogen 15, and it has an I that equals 1/2. That makes it a nuclear dipole, which is easy for us, right? But the only problem is, though, is that nitrogen 15 is actually very low abundance, right? super low natural abundance, because the vast majority of the nitrogen in our atmosphere, right, or in the universe, is actually nitrogen 14, not nitrogen 15. So its natural abundance is, that was supposed to be an at sign. There we go. Is at 0.389%. So a very tiny amount. So you might be asking yourself, why do we even study it then if its abundance is so low and it's not helpful? Well, actually, that actually is very helpful, because it's most commonly used in my favorite NMR technique, which is protein NMR. Commonly used in protein NMR. Not proton NMR, but protein NMR. And the reason why is because recall that a protein or a peptide is held together with a peptide backbone, and the peptide backbone, every peptide backbone has amide bonds, and or the peptide bond, right, for every amino acid there, and they all contain a nitrogen. And so we can do very fun, very interesting experiments where we can use NMR to this thing called solution NMR to watch a protein change its conformation due to conditions like interacting with its environment or interacting with its substrate. And the peaks will change, right? Because we are studying the movement of the nitrogen 15s in the backbone, right? But again, it's very, very low abundance. So how are we able to study protein conformations with it on NMR? Well, the reason why we can do that is because we can, when we're growing our protein, well, let me rephrase that. When we're growing our bacteria that are expressing our proteins, like you learn how to do in biochemistry, instead of giving it a normal media, we can actually give it an enriched media that's usually usually includes nitrogen 15 ammonium chloride, right? And so when we include this nitrogen 15 ammonium chloride in the growth medium, the bacteria will eat that, and it will incorporate the nitrogen 15s into their peptide structure, right? Their peptide backbone, and so now every single peptide bond in a protein, right, will have nitrogen 15 labeled in it, right? So we call this isotopically labeling, isotopically labeled all right, and that's with nitrogen 15, or for short N15 ammonium chloride, enriched media, right, during protein expression. During protein expression, right? And so we'll call this an N15 labeled protein. Which I actually did a lot of this when I was in grad school, right? All right, so let's keep on going with some other nuclei. Next we have oxygen 17, which has an I of 5 halves. And so this is a nuclear quadrupole. Again, right, most of the oxygen in our universe is oxygen 16, not 17, so this guy has super low abundance. At about 0.04%, right? So not super helpful because it's really, really low abundance. But The good news, though, or not the good news, but even if it was abundant, we wouldn't be able to use it anyway because it experiences since it's a nuclear quadrupole. It experiences thing called rapid relaxation, not rabid like a dog, but rapid relaxation. All right, and rapid relaxation is caused by is a result of the uncertainty principle. I'm sorry, it's not a result of the uncertainty principle, but is explained. It is explained by the uh, uh, it prevents sharp lines on the NMR, and this is explained because of the uncertainty principle. Why does that look so bad? I'm gonna write the whole thing again. This is explained by the uncertainty principle. Right? And because of that, this is not typically studied. This nuclei is not typically studied, right? So let's talk about another category of nuclei. That's even mass number nuclei with even atomic number. And so that would include things like our normal old carbon 12, right? Normal old carbon 12 and oxygen 16. Okay. These guys, though, they have an I equals 0, which means no nuclear spin. And not NMR active. Right? Not NMR active. Not NMR active. And then our last category is even mass number with odd atomic number. Odd atomic number, right? And so this includes things like deuterium or even nitrogen 14, the most common. These guys have an I that is greater than or equal to 1, right? Greater than or equal to 1. And you've actually seen, if you've done a carbon 13 NMR before, you've actually seen the manifestation of this before, because when a very common solvent that we use, every solvent that you use for NMR is a deuterated solvent, right? And so, meaning that it has, in place of hydrogens, it has a deuterium. And deuterium's I is equal to 1. And so that means that it has its spin states include -1, 0, and 1. And so the -1 here is, you can think of that as being the spin down. And then you can think of the positive one as being the spin up. And then the 0 is spin 0. Right, spin 0, right? And you can see then that the deuterium has 3 spin states, right? 3 spin states. What's really cool about that is that it manifests itself on a carbon-13 NMR, because a very common solvent that's used in NMR in general is chloroform D, or deuterated chloroform. And I know that in the Pelfrey lab you guys use a lot of DMSO, but an even more common one is chloroform D. And so chloroform D is CdCl3. And first thing to note is that this carbon right here, right? Let's talk about its abundance real quick, because we haven't talked about it. 98.9% of all carbon atoms are carbon-12, right? And then the 1.1% are carbon-13. They're carbon-13, right? And so what happens is that when you run whenever you run a carbon-13 NMR, and whenever you run a carbon-13 NMR, and you're using deuterated chloroform, or chloroform D, right? You can actually find the peaks for the deuteriums on the NMR at around 77 ppm. But you're thinking to yourself, wait a second, I thought the reason why we use deuterated solvents for NMR is because they're not NMR active, and so that's why they don't interfere with our sample, right? They don't have protons, so they won't interfere with the protons of our samples. That's actually not true, right? And everybody makes that mistake. Deuterium is actually NMR active, right? But it's just NMR active at a very different range of where you would be working on doing a proton NMR, right? When we're doing proton NMR, you're at like 0 to like the low teens ppm, right? In the teens ppm. But if you notice here, right, the triplet peak here of the deuterium, the deuterated chloroform, right, is at 77 ppm, right? And so deuteriums are actually active, NMR active. They just are not NMR active in the same area in the same chemical shifts as the proton NMRs are, right? Or the protons are. So the other interesting thing, though, like I was saying before, you've seen the manifestation of this -1, 0, 1 spin states of deuterium, because each one of these peaks here represents, this is what we call a 1 to 1 to 1 triplet, right? Triplet, and it actually represents the deuteriums that are attached to the carbon-13s of chloroform D, right? So that's pretty cool. That's really neat. Okay. On the carbon-13, I promise that says carbon-13. Alright, NMR. It's pretty neat, right? It's pretty neat. Yep. So three spin states here represents the 3 peaks, right, on the carbon-13. for chloroform D that are attached to the carbon 13. Right. So let's go ahead and now I would like to just kind of put it all into context by talking about energy differences, right? And so the energy differences in spectroscopy. Okay. And so if you recall from when we were talking about IR, UV vis, and fluorescence spectrometry, right? The energy differences between the normal state and the excited state are very large. Okay, so with IR, UV, vis, and fluorescence, the energy gap is very large, right? But compare that to nuclear magnetic resonance, right, or the nuclear transitions, right? Because remember that in IR and those higher energy ones like UV vis and fluorescence, we have like electrons moving, right? Uh, Electrons moving, but at the nuclear level, right, it's very, very small energy. Remember that back in the very beginning of the semester, we were talking about how nuclear is only really active at the radio frequency, which is very low energy, right? So, contrastly, the energy gap between the alpha and beta states of an NMR of NMR very small, are very small in comparison. So it makes NMR highly insensitive. So generally, you need a very, very concentrated sample for you to be able to even detect anything without, it being like lost in the noise. Especially for those nuclear those nuclei that are lower magnetogyric ratio, which we'll talk about that later. But those include like carbon 13 and things like that. So let's kind of talk about this in a physics context, right? If we have an energy right here, if we have energy, and we have two states, the ground state and the excited state. But in NMR, we would call this the alpha state, and then the beta state. The gap here between these two states is known as the change in energy, right? So this is the energy gap. Right, that's the energy gap. Oop, I forgot the N in there, sorry. There you go, that's the energy gap. And so again, if we apply a magnetic field, right, which is going to be B0, B naught, right? This B naught is also, we're also going to note it as being the strength of the magnetic field. Magnetic field strength, right? When we apply this magnetic field to this to the nucleus, right, we either get it aligning with the magnetic field at a lower energy state, the alpha state, or aligning against at the beta state, which is the higher energy state, right? And so we're already super familiar with this equation, right, which is E, the change in E, right, equals Planck's constant times nu, right? And so nu here, right, is a radio frequency, of course, because we already talked about how for nuclear transitions we're in radio frequency range, right? Something like something like 600 megahertz thereabouts. We get all the way down to 60 megahertz, 30 megahertz, but pretty low, right? And so, uh, the way that we can calculate what the energy gap is between these two states, right? The way that we can calculate what the energy gap is between these two states, the alpha and the beta state, is we have an equation, right? That is dependent on this next thing here, which is gamma. And gamma is the magneto-gyric ratio. Although sometimes you'll hear me call it the gyromagnetic ratio, but it's actually, I've heard it said both ways, but magneto-gyric ratio is probably more common, right? And basically what this is how big the nuclear spin is. How big is the nuclear spin, right? And so the equation that we can use now to figure out what this energy gap is between the alpha and beta state is the change of energy equals gamma, or the magneto-gyric ratio, times the B naught, which is the strength of the magnetic field, all divided by 2 pi. And so what you can see here is that the strength of the magnetic field is actually in the numerator, right? And so that means that the stronger the magnetic field, right, the bigger the energy gap. And the bigger the energy gap, the easier it is for us to detect using an NMR instrument, right? So the bigger the B naught, the bigger the energy gap, right? Thus, the bigger the magnet, the bigger the better, right? And so let's just kind of give us some context as far as numbers go, right? Or what it means to have a big magnet, right? If we had a magnet that was 70,500 Gauss, I spelled Gauss wrong. It should be G. Is it GU or GA? Oh, whatever. Who cares? Maybe it's GA actually. Yeah. If we have a 70,500 Gauss magnet, and then we were doing proton NMR, that would yield us a 300 megahertz instrument, right? If we had a 188,000, nope, I skipped one. If we had a 117,500 Gauss magnet, that would give us a 500 megahertz instrument. And if we had a 188,000 Gauss magnet, that would yield us a 800 megahertz instrument. So at this point in time, the highest field instrument we have is probably around a 1.2 megahertz instrument, and so it's really interesting because, NMR spectrometers are like really pushing the limits on with their electronics, right, on how to create a uniform magnetic field, homogeneous magnetic field, because you kind of want to keep the magnetic field the same throughout the entire sample, because if you don't, you'll have different readings for every part of your sample, even though it's supposed to be a homogeneous mixture. And so, the best magnets there are now, right, are around $10 million, and they're around $10 million, and they're running at 1.2 gigahertz, right, or maybe or 1,200 megahertz. So they're really high field instruments. Compare that to the instrument that we have in our lab, which is only 60 megahertz. So we have a pretty low field instrument compared to the big fields. So Auburn had a 600 megahertz instrument. That was the highest they had. I'm pretty sure Texas A&M has a 1 gigahertz or 1,000 megahertz instrument. They're really big though. The one in Auburn, you had to climb up a ladder and then load it from the top, and it was crazy. But the one at Texas A&M, you actually have to go to the second floor of the facility and then walk across a bridgeway and then load it from the bridge because it was so tall. But yeah, pretty interesting stuff. So I want to end up with just kind of putting all this stuff into context. So energy and context. All right. So we talked a second ago about UV and the energy that's involved in UV. So let's just say UV at 254 nanometers, right? If you were to use the equation that we just talked about here, this one right here, and converted that to kilocalories per mole, we would get a change in energy that equals 113 kilocalories per mole. And we've already talked about this before, but this is the kind of energy that's involved in electronic transitions, right? In UV vis and fluorescence and such. And it's also the kind of energy that's involved in breaking bonds, breaking and making bonds, right? So electronic transitions, okay? Then right under that, we have IR, right? And we'll just use a very common stretch here, which is a carbonyl stretch. That's at 1700 wave numbers, or reciprocal centimeters, right? If we do the calculation and convert it to change in energy in kilocalories, this actually corresponds to or equals to 4.87 kilocalories per mole. We're still in the same unit, kilocalories per mole, but IR, as you can see, is much less energy gap than there is in UV, right? And so that's pretty interesting, right? Again, these are in IR, it's the vibrational transitions, right? And so that's the one with the wagging and the scissoring and all those things, with the hand wavy things, right? That's what that is. Let's compare that though to NMR, and proton NMR at that, which is the most powerful of the NMRs. Not powerful like the most powerful is in method, but it's the one that has the highest energy gap, right? This guy here, if we were to use a 500 megahertz instrument, we converted that to a change in energy in kilocalories per mole, and we get a minuscule 0.0477, and wait for it, it's calories per mole, not even kilocalories per mole. So really, really tiny, right? And these again are the nuclear transitions, or the transition from the alpha state to the beta state. And so again, this is just based on energetics. You can see how NMR are super, super insensitive compared to the other methods, right? And so the absolute last thing I want to talk about here is just kind of again, putting things in context. Let's talk about the different magnetogyric ratios, right? Magnetogyric ratios, right? And so we've been talking about proton NMR again for a while now, and it's because it's the most commonly used and it's the most easiest, right? Because it has the biggest energy gap of all. The magnetogyric ratio, right, is a constant for different atoms. Different atoms have a different, different nuclei, isotopes have a different uh, have different gammas, right? And so protons in general, they have a very high gamma at 26,753, right? And so if you were to use a 117,500 Gauss magnet, and we already said this before, this would give you a 500 megahertz NMR, which is interesting because oftentimes we use the term when we say we have a 60 megahertz NMR or a 500 megahertz NMR or 600, that only applies to a proton NMR. So when you're saying I did like a carbon 13 NMR on a 500 megahertz, you actually didn't do that, right? Because carbon 13's magneto-drag ratio is much smaller, and remember that's a part of the equation, right? And so for carbon 13, we actually consider what we call this a low gamma, right? I'll just put this right here, just to remind you, this is a low gamma, right? Proton is a high gamma nuclei, but carbon 13 is a low gamma nuclei because its magneto-drag ratio is only 67/28. And at the same strength magnet, we only get a change in energy or a gap of 125, effectively a magnet of 125 megahertz and 0.74 megahertz. All right. Let's look at a few other ones here. We have fluorine 19. Fluorine 19 is like proton. It's like 25,179. And so applying the same strength magnet, 117,500, we get 470.58 megahertz. So pretty close to doing a proton NMR, but not exactly, right? Phosphorus 31 is kind of a mid. It has a magneto-drag ratio of 10,840. So on a 500 megahertz instrument, you're actually only getting out of it effectively 202.59 megahertz. And then lastly but not the least, right, we have another low gamma. I'll have another low gamma with deuterium, right? And so deuterium is actually very low gamma, lower than carbon 13 at 4,107. And when you do an NMR on it, using a 500 megahertz, you're effectively only getting 76.76 megahertz. All right. Well, that ends today's lecture. So I'll see you back again on Wednesday for the second part of this lecture. Right? Have a good week.